let's start the presentation. I'm Seokwoo Choi from South Korea, and today I will present about API deobfuscator, which identifies runtime-obfuscated API calls via memory access analysis. First, I will introduce what is runtime API obfuscation and why it matters. And second, I will explain my algorithm to solve the problem and explain the details of my implementation and how it works and show my demo. I'm targeting especially the Packer Themida because as far as I know, it is the only packers that use runtime obfuscation technique. And runtime API obfuscation is done on dynamic. Obfuscation techniques can be classified into static and dynamic. Static obfuscation, once a code is obfuscated, it never changes because it's static. And dynamic obfuscation, embedded obfuscator, that is embedded during first static obfuscation, and it changes the code during each run. For example, when we obfuscate our example program and with Themida, and this example is about VM protect. VM protect does not use runtime obfuscation technique, so we can analyze it more easily than Themida, although it is using code virtualization to protect API call. But when we set breakpoint on API function, then at last we can reach the API function itself, so we can analyze it more easily. And the code never changes during runtime. But Themida changes its code each run. So as you can see in the picture, when the first time message box API is obfuscated, it has many split basic blocks. And when we run second time, it changes shape because Themida embeds some runtime obfuscator in executable file. Furthermore, it is more hard to analyze Themida packed executable because the call instruction is changed and the address call target is changing. As you can see, the original program was calling message box API function, and after Themida unpacking, the packer changes the call instruction, and the call target is changed to 0040000. And it changes, the call target address changes each run. And when we set breakpoint on message box, we cannot check the message box because the message box function itself is not executed. So we need to identify the code which is running belong to which function, originally which function. So when I first noticed the Themida is using runtime obfuscation technique, first I set breakpoint on API function that is contained in the obfuscated API function. For example, if I set breakpoint on load library exa instead of load library A, which is I want to analyze, because load library A calls load library exa, so when we set breakpoint on load library exa, then we know that some obfuscated code is running. Load library exa, and for write file, if we want to check write file, we know that write file calls ntdll.gw write file. So we set breakpoint on gw write file, and we know that write file is running. This works, but it is not always precise because other functions also call, for example, gw write file. So we need more precise analysis method. So second, I try to optimize obfuscated function code, and I compared each optimized function with original functions. I found that it is precise, more than 90% matches very well, but some functions are very short and hard to optimize, so I need more easy method to deobfuscate API calls. So finally, I try to monitor API obfuscation process. I monitored API obfuscation process using a memory tracer. I built it using Intel Pin. So I recorded every read and write, especially memory read on API functions. As you can see in the picture, the first column means the instruction address, and the second column indicate read or write, and read or write on some address. And the next column is the size, and the next column is module and API function, and the last one is the instruction executed. As you can see, the address, the message box A address starts from 757D27 CE, and the read address is increasing one by one. So 757D27CF, one byte is read, and 757D27D01, it is read one by one. And we look at the memory trace again and again, then we can find the API obfuscation process. For example, message box A code is copied to a temporary buffer. The embedded obfuscator expands, obfuscate the instruction, so it becomes very large. And from the temporary buffer, it is split to many basic blocks, and the small basic block is mixed with other functions, so it is very hard to identify from the small basic block what this code is belong to. And finally, after the API obfuscation end, the packer finally changes the call instruction. The call target is changed to the first address of the obfuscated function, and sometimes the function is called via register or indirect call. So we need to change. They change the import address table to obfuscated address. We need to identify the address. In this picture, 40.0.1000 belong to what originally what function. So to identify functions, I observed each function is obfuscated in sequence. And for each API function, every instruction is read and obfuscated instructions are written. We can divide by time. So in the picture, when the obfuscator read ws to winsock.bind, every bytes of winsock bind and write obfuscated code. It is divided. And next, winsock connect API function is read and it is written to other memory addresses. So I related memory reads on API function code and corresponding memory writes on obfuscated code. That is building a map from addresses of obfuscated API function to original API function addresses. Then we recover original API function by the obfuscated call target address. If we want precise analysis, maybe it is very complex and hard because code is obfuscated. First I wanted to build some value-dependent analysis on every memory read, but it was so complex, so I used an approximate algorithm. As you can see in the diagram, obfuscated function instruction addresses contain one obfuscated API call target address, and obfuscated function instruction addresses are contained in write addresses before the next API function reads. So we record every memory write before the next API function or DLL, read on DLL, next DLL. And this algorithm has some problem because the last API function, after the last API function obfuscation, we don't know when it ends. So I limited the number of memory write to about 10,000. It worked. And there are some overlapping addresses. Temporary buffers are shared. So write addresses, for example, get temp file name and get temp path. That is obfuscated sequentially, and its address overlaps. Write address overlaps a little, but obfuscated get temp name code addresses and obfuscated get temp path code addresses doesn't overlap, so it's safe. So I implemented the memory access analyzer as an Intel pin tool. It records memory reads on API functions and records memory writes on newly allocated memory block. And it constructs a map from each API function to memory write addresses, which is a superset of obfuscated code addresses. And the tool poses at OEP, original entry point. It is not exact OEP, it's near OEP. And finally, it identifies API icons. We need OEP detection algorithm. In many previous papers, it defines the algorithm to find OEP as to find the address that is written and executed. But Themida, as regarding Themida hacked files, it write and execute and unpacks another packer in it, and it packs again and again. It changes code again and again, so the algorithm is not working. And so I used some heuristics, and I thought that the last executed address that is written is OEP. So And I checked written memory blocks instead of using the exact addresses to save memory because Intel pin tool shares the memory with the original executable. So I found OEP. And after I find OEP, I tested it with only debugger with some plugins to evade anti-debugging techniques in Themida. And I add the OEP, set hardware breakpoint on OEP and run, ignoring some exceptions. Then we can reach, this is the win main of my tiny example. When we find intermodular calls, that we can find that many addresses are newly allocated blocks. And it contains some indirect address. So I resolved the address using the built map and generated a text file. It contains original entry point and address and some information that need to be changed after OEP. In this picture, address means the address in the IAT need to be changed, and call means the call instruction need to be changed to this, and the address is in RBA because of ASLR. And I wanted to debug the deobfuscated binary. There are two ways that we can attach our debugger post at OEP with the pin tool. But it is very hard to attach debugger because Themida use anti-attach techniques, and I need to build the anti-attach techniques that many debuggers use with pin. So I managed to write some code. I need to protect ntdll.dbg UI remote break-in and breakpoint from patching and prevent some setting flag. And when I run one thread program, then more than 24 threads are monitoring whether someone is monitoring the program. So I need to disarm every monitoring thread. So it's very hard, but it's possible. So instead I generated a debugger script to resolve API calls. The file generated by the memory access analyzer contains OEP and resolved obfuscated addresses. And I implemented a Python script to generate a debugger script that execute on the OEP and resolve obfuscated addresses. So this is the result. The syntax is weird, but it works. And after resolving the obfuscated API call, call to allocated address change it to the API function we know. So I will show you some demos. I downloaded the file from VirusTotal this morning. It is a big malware that has many features, agents, Trojan agents. I don't know exactly what it is, but because it is written in China and Chinese characters. So the UI is text, so it is very hard to use. But I'm accustomed to it. So, but it takes 2 or 3 minutes to deobfuscate the binary because I read every read and write instructions. But if you have been some experience using pin tool, pin tracer, for example, we can use STE instead of building pin tool. The tracer generates 2 or 3 gigabytes for a simple binary. So it is not so big compared to other instruction tracers. While it's running, I will explain other slides. My tool has limitation because it is depending on pin. Last year, someone told that pin detection is possible. So we can detect someone is using pin. If it is possible, then it is easily broken. And some malware holds on the pin. Pin has some defects, but it is not open source, so I cannot fix it. And I use memory access patterns, but it can also be changed. But I think it is very hard, but it can change it. It can be changed. And it does not deal with the virtualization macros. So I need to do it in the future. Still running. And I need to build Deobfuscator based on emulators instead using pin. And the tool has some defects because I am not good at reverse engineering. So it ended in 2 minutes. I have 4 minutes, and the result is like this. This malware is very many calls. Oh, sorry. Wait a moment. Okay. I didn't notice. And it has many obfuscated calls, and I resolved everything. And it can be converted to only debugger script using and I generated only debugger scripts, and it can be run under only debugger. And we can run the script, and it execute, and it contains some obfuscated address, and after the script is executed, then the address is resolved. It contains more than 1,000 API function calls, so it takes time. You can see the obfuscated call is resolved. You hit create, and we can debug using step. And also, we can dump this file. We know the original entry point by the text file generated. And we can easily find the IAT. Yeah, it has some problem, but we can download it. And with either, yeah, I will show the pre-made either program because it takes too long. So we know what is this application. We can see some shell code and some dangerous code. We can find some IP addresses, and all input table is recovered, so we can easily analyze, and even we can use hexarray decompiler to analyze it. So that's all. If you have any question. Yeah. Oh, sorry. Any question? Mm-hmm. Mm-hmm. Yes. Yeah, it's patching. Yeah, then we need to fix it by manually. If you have questions, mail me. The last slide I have mail address.